Hello students, today we are going to discuss forced oscillation and the condition of resonance. Many times you have seen so many practical examples where a particle is executing simple harmonic motion or an object having a mass. An object having a mass executing simple harmonic motion, and after some times its oscillations are damped and finally it stops to oscillate. The reason for that is there are some damping forces which are preventing the oscillations of that particle. These damp force may be air friction, maybe some another damping force of that medium in which the oscillations are produced by that particle. If there may be a condition to prevent the damping of the oscillation of that particle executing the simple harmonic motion, in that case what can we do? An external force can be given to that system which is executing simple harmonic motion, and and its damping of the oscillation can be reduced or can be prevented by applying an external force to maintain its oscillations continuously. In this manner, the external force which is determining the continuous oscillations of that particle is called an external force, and the oscillations produced by this particle due to external force is called the forced oscillation for that particle. Just consider a simple example. A person is swinging without any external force. Provided to him. What will happen after some time? The amplitude of swing decreases gradually, and the person, also the swing system, comes to rest. Now, no oscillatory movement of that person or the swing is there. Now, if an external force is applied to the swing system, its oscillatory motion the oscillations of the system can be made continue. System can be prevented to come at halt. For a proper oscillatory motion, the external force applied to it should also be a time varying function, and this type of simple harmonic motion, forced or driven oscillatory motion. Now there may be two conditions. Then that and on applying an external force, the system may oscillate at its natural frequency that will be equal to the external force. In that case, the frequency of oscillation of the system and the frequency of the applied force externally will be the same, and that condition can be treated as a resonant condition where the frequency of driven force and the frequency of oscillatory system is same. And if the frequency of oscillation for the external force and for the system both are different, then it will be another condition where the resultant frequency will be the different from the resonant frequency. So we will discuss both of the conditions. First, here we are saying that the at first consider that a system is executing simple harmonic motion under the impact of damping forces such that net damping forces net damping force is equals to multiply by x as a function of time minus b multiply by v as a function of time, where minus kxt is a restoring force which finally prevents the oscillation of the system and restore it at its mean position or initial position, and minus b vt is another force, another damping force which also is preventing the oscillations of the system by providing it another type of damping force. Say in a previous case where a spring mass block system connected to a vane and vane was submerged in a liquid. In that case, the damping force provided by the liquid we have taken here by minus b vt. So we are considering here that the system is executing a simple harmonic motion under the impact of two damping forces. One is the restoring force and another is another type of damping force. Now in that case, if we need to make the system not to damp and to oscillate continuously, in that case we have to provide it an external force. Let us consider that external force to prevent the damping of the system. The external force applied to system to prevent damping of the oscillations and to maintain an oscillatory motion of system continuously. It can be expressed as the external force f as a function of time. Since this external force will act against the net damping force, so the complete force experienced by the system will be such that it will be the algebraic sum vectorially the net force acting on the system, the net force acting will be now F net equals to F naught cos omega t minus kx t minus b vt. Or the same equation can be written as ma t equals to F naught cos omega t minus k x t minus b vt. Finally, we can write this equation in terms of the displacement x or the amplitude, as it is known as amplitude, the displacement from mean position. We can write it here in terms of amplitude of the oscillatory system, m d square x f naught cos omega t kx dx upon, thus the external force on the system f naught cos omega t equals to m d square x upon dt square plus b dx upon dt plus kx, where m is the mass of that system executing oscillatory motion or the simple harmonic motion. Again, the same equation can be written as the external force as a function of time equals to m d square x upon dt square plus b dx upon dt. So this is the equation number 1, which represents the oscillatory motion of a particle having mass capital M, and an external force Ft, which is periodic, is applied to the system which is oscillating at a frequency. Initially, the oscillator will oscillate at its natural frequency, and after some time it will be driven by the frequency of the applied force externally to the system. So the amplitude of the particle executing simple harmonic motion, or you can say the amplitude of the system executing oscillations after the natural frequency die out, its displacement is given by, as a solution of this equation, amplitude of the system after application of external force will be given by xt equals to where A is the maximum amplitude of the system and omega is the frequency of that external force which has been applied here to the system to continue its oscillatory motion. The amplitude A is the function of force frequency omega, and its value is given by, which has been found analytically, A equals to the maximum value of external force divided by the term in square root, that is m square omega naught square minus omega square plus omega square b square, where omega naught the natural frequency of the system and omega is the force frequency. So thus an oscillatory system can be made to continue its oscillation by providing it an external force. So its oscillation will not be damped down and we can maintain its oscillation by applying an external force to that. Next, we will discuss the two cases relevant to this condition where an external force is applied to a system which is executing a simple harmonic motion. Till then, good day.